All right, welcome to class, everybody. So we're now into the second, well, like sort of the last third of chapter 3, which is we're going to be wrapping up one-dimensional conduction. So last week we started talking about generation and the implications of having generation. So you're still solving the heat equation in one dimension, but now you get this extra generation term, and typically that'll just be a constant, although it doesn't necessarily have to be. But that, so we're talking about heat flow through a plane wall. That makes it so that our temperature profile is no longer just this simple linear thing because we're generating energy throughout the solid as we go through. So that adds some curvature to our line, and one of the implications is that you can no longer use the thermal resistance method through a solid or a solid medium that has generation in it. The same kind of results apply for radial systems, so whether it's cylindrical or spherical. We're still solving the heat equation in one dimension, but now we have this extra generation term in there. So you can go through and do integrations yourself, certainly, and solve for the temperature distribution. If certain boundary conditions apply, you can actually look up what those solutions here in table C1 and C2, which is in the back of the book. So same kind of an idea as we've talked about with one-dimensional conduction when there's no generation. We talked about the plane wall, cylindrical wall, and the spherical wall systems, but now you just add in generation. That makes things a little bit more complicated and just a little different. Any questions there? I also want to point out the video did not save for Friday, so we didn't have a video from that one. Okay, so now we're going to get into something called extended surfaces. So often you want to increase the surface area. If you remember Newton's law of cooling, that HA times delta T, if you have a bigger area, you'll be able to transfer more heat. So often you'll design a system that has extra surface area, and that's designed to help improve heat transfer. So there's something called an extended surface, and that is where you have a big chunk of, let's say you have a big chunk of metal, and you want to increase the amount of heat transfer if it's convecting out to the environment. So you may add on little things called fins or pins onto there. So that just increases the surface area. So that's what we're going to be talking about now. So these are what some of these fins or pins might look like. So you might have just a straight rectangular prism coming out of a solid. You might have something that's more of a triangular prism. You might have disc shape or cone shape. But all these things would be just to increase the total surface area of that solid so that when it's convecting back out into its environment, that you have more surface area and you increase the rate of heat transfer. So the reason that these show up in, well, we'll get to this. So there's actually, when you have if you can make the assumption that heat transfer is still one-dimensional, and when it's steady state and has constant conductivity, and when it has a uniform cross-sectional area, meaning that fin poking out is all, it doesn't change in shape, then you can actually derive this equation. This is called the fin equation. So it looks familiar in form to the heat equation. It's actually a little bit different functionally, and we'll explain why. You can get this into a different form by combining terms and having this reduced temperature where theta is just equal to your temperature minus the ambient temperature, and that just makes it mathematically a little simpler. It makes the integration easier, so you'd get a term that looks like that. Then you can solve this equation to get the temperature profile all the way through your fin. So just because I really like emphasizing being able to do this differential energy balance, we're going to go through and talk about where this equation comes from, and I would appreciate any comments or help as we go through this. If you'll just give me a moment. Okay, so I hope you're starting to get a theme. You should have had a lot of this on your last homework where you're going through and deriving these equations for yourself, but it hopefully for those of you for whom it's clicking, you're realizing these are just energy balances. And once you get into the flow of doing these energy balances, you can derive all sorts of equations, and they can be quite powerful. So let's say we satisfy all of those assumptions. Again, one-dimensional, and we'll hit on that again. Steady state, constant conductivity, uniform cross-sectional area. I forgot to mention we're also going to neglect any generation and radiation, and that allows us to get to the Finn equation that you see there. So the way we'd go about doing that is we would assume that we have some sort of base. So here's our base. Then we've got this long fin sticking out from there. So this problem is, we're going to make it a one-dimensional problem. And we're going to do that by assuming that temperature varies only in this direction. Let's call this the x direction. So is this, if we want to be as rigorous as we can possibly be, is this really a one-dimensional problem? So why not? Okay, I see Titus showing that temperature is probably going to vary in this direction as well. So we're basically neglecting temperature variation in that direction. And what about this system allows us to neglect variation in the, let's call this the y direction. This could be the r direction if this were cylindrical in shape. So what would allow us to neglect any temperature variation in the y or r direction? Okay, so it's very thin. So because this is very thin, we're going to expect that heat can conduct through this in this direction quite rapidly. But in this direction, it's obviously going to start at this base temperature. So let's assume this is really hot. And then the longer this thing goes out, it's going to approach the ambient temperature of T infinity. So we definitely expect that dt dx is some finite number. And if this were a hot system, we'd expect that dt dx is going to be negative. Or if it's a cold system, we'd expect dt dx to be positive. Then for dt dy or dt dr, we're just going to neglect temperature variation in that direction. So this is an approximation that we're making, which will make these equations much easier to deal with. Otherwise, we're dealing with a two-dimensional problem. So inherently, it is a two-dimensional problem. We're just going to neglect one of those dimensions because we expect the effects in the direction along the length of this fin to be much stronger than the effects than the temperature change going radially. Questions there? So that's an important assumption that we're making. We're assuming that it's isothermal in this direction, the radial or the y direction, and that the temperature is varying quite drastically in the axial direction. Okay? So how do we go about deriving an equation like this? Okay, an energy balance. So let's say that we actually want to solve for the temperature profile down this whole thing. So if we want a temperature profile, we want to know what temperature is as a function of x down the whole length of this thing. So that means we're going to take a differential energy balance, and we're eventually going to shrink our dimensions of that differential energy balance down to 0 and turn this into a differential equation. So we would do that. So we would take a control volume. So we take a shell or some little slice out of this thing and just give it an arbitrary width of delta x. Okay, so then we would do our balance on that section. All right, so let's just go with the full generic energy balance. So we're going to have accumulation. We're going to have in, out, and generation terms. Okay, so we're doing our energy accounting over this little slice of this fin. So how is energy getting in? Well, actually, first of all, what's our accumulation term? 0, because if you remember, one of our assumptions was that this is at steady state, so we don't have to worry about accumulation. Okay, how does energy get into our little finite volume? Yeah. Okay, so it's conducting actually not from the, well, ultimately it's coming from the base, but really for this particular guy, it's coming in just from right here in the adjacent section. Great, thank you. So we're going to have conduction coming in. So that is going to be coming in by Fourier's law. So minus k dt dx. And let's assume this thing is square in shape and that it is delta y deep and delta z tall. So we could just have a delta y, delta z. Okay. How is energy getting out? Great, excellent. So it's getting out by conduction here also. So again, we're going to have a minus k. Oh, and this, sorry. The in is evaluated at the left boundary, just at x. Then out we have minus k dt dx times delta y times delta z. And that's evaluated at x plus delta x. So when we have another out term, so it's also going to be losing energy by h, so by Newton's law of cooling. So here we have h times our area, and I'm going to express our area as delta x multiplied by the perimeter. So in this case, the perimeter would be, you have the two sides of delta y and the two sides of delta z. So the perimeter would be 2 times 2 and then parentheses times delta y plus delta z. Okay, and then we're going to have the temperature of that little section minus T infinity. And I erase the generation term, which is going to be 0 because we're assuming no generation. So we don't have to worry about generation or accumulation. So if we go ahead and compile our system, we could, let's see. Okay. Oh, I only gave myself one sheet to do this. All right, so let's do this. I'm also going to make life a little bit easier by saying that our cross-sectional area, delta y times delta z, we're just going to define as a sub c. So that's our cross-sectional area. So if we gather our terms and put this into equation form, we get k times our cross-sectional area multiplied by dt dx as evaluated at x plus delta x minus dt dx as evaluated at x minus h times p times delta x times t minus t infinity all equals 0. So then hopefully you're getting a sense of this procedure. Then we would divide by the thickness of our little section and take the limit.
What's that P there on the, isn't that neutral and cooling?
Yep. So that P is the perimeter. So the total area, you're going to have to account for all 4 sides of this if it's square in shape. So that would be the total perimeter multiplied by the thickness of it. Okay, so then we would get this down. We would take the limit as we go down. So you're going to see that a second derivative is going to pop out of here. So we get k times AC times the second derivative of temperature with respect to x minus HP times T minus T infinity. And that all equals 0. And then there's another form. If you just want to lump your constants together, you can just divide everything by k times AC, and you get d squared t dx squared minus HP over KAC t minus t infinity, and that all equals 0. Okay, so this is just a differential equation. This is called the fin equation, and it applies whenever you have a really long fin, and you can make the approximation that temperature variation in the radial or in the y or in the z direction are negligible because it's so thin. You really care about how temperature changes down the length. So again, that's an approximation. So this thin fin equation is just an approximation. If you really wanted to be rigorous, you could keep it as a two-dimensional or even a three-dimensional problem and find a much more complex solution to your problem. Any questions so far? Okay, so just like with the heat equation, in one dimension, you could go about just separating and integrating. This one actually the math gets a little bit more complicated, and it's not quite as easy to do these integrations in your head. So you can just go to solutions. So if you have this base condition, which is a boundary condition, you're just saying that the temperature at the far left of this thing is equal to the base temperature. Then you will have different tip conditions. So here's the tip. So you can either assume that you're also convecting from that tip. You can assume that the tip is adiabatic, which means that your temperature change with respect to x is just equal to 0. It could be insulated at the end. You could assume that it has a fixed temperature at the end. Or you could assume that it's just infinitely long. And eventually, your reduced temperature is equal to 0, which just means the tip of this thing just equals ambient temperature because it's so long. So there are 4 different conditions. And when you solve that equation under these 4 different conditions, you get 4 different solutions. And I hope I have this. I'm going to skip ahead. Okay, so I personally don't care about your abilities as much to integrate that equation. But you can go to this handy table in your book, table 3.4, for those of you who have the 7th edition, and I don't know what it is for those who have the 8th edition. But there's a table in here that gives you solutions to this fin equation. So we have these different cases. So notice that here are the tip conditions. So we can have convection happening at the tip. It could be adiabatic, it could be a fixed temperature, or it could be an infinitely long fin. And then depending on our tip condition, our temperature distribution is going to look different. So these are really just plug and chug type problems. The equations look kind of nasty, and you notice they have these other variables in there that you may not know what they mean. So the first thing to think about is this temperature distribution is given in terms of your reduced temperature, theta over theta b. But you can find that the definitions of those things are just down here. So theta, again, is just the temperature at wherever you are along the fin minus your ambient temperature. Then theta b is just your temperature at the base minus ambient temperature. And then mainly out of convenience to make the integrations easier and to make the equations look a little bit cleaner, we have our intermediate variables are just defined as a function of those variables that we've talked about. So our heat transfer coefficient and our thermal conductivity, our cross-sectional area, and our perimeter. So from those equations, you can also get this fin heat transfer rate. So if you know that you can make all those assumptions, that it's a one-dimensional system where the cross-sectional area does not vary, constant thermal conductivity, no generation, steady state, then you can just look up these equations and you can immediately solve for your temperature distribution and the total amount of heat that an individual fin will convect out to the ambient. So we'll get back to that. So we've added these fins to some big solid because we want to increase heat transfer. But because those fins are long and we see their temperature decay the longer they get, they're not perfectly efficient. So especially if you considered a really long fin. So if we consider a really long fin, at this left end it's going to get really hot. At the right end it's going to be much less hot and closer to ambient temperature. So as it gets closer to ambient temperature, the driving force for heat transfer at that end is a lot lower. It's a lot closer to ambient temperature, so there won't be as much heat per unit length happening at the far right end, which basically I'm saying this to make the point that these aren't perfectly efficient. Having the fin means you drop in temperature, which means your driving force goes down. So we define something called the fin efficiency. So the fin efficiency is, we're using this Greek symbol eta. So eta sub f just means the efficiency of the fin. That's defined as the amount of heat that actually goes through your fin divided by the amount of heat that would go through your fin if your fin, 100% of it were just equal to the base temperature. So the best you could possibly do in terms of having a perfectly efficient fin would be if your fin were a perfect conductor and the heat immediately propagated through it and then convected out to ambient. But that's not the case because having a material that is a perfect conductor is not possible. So if you look, the way to solve for the fin efficiency would be to apply one of those equations from the table and then calculate how much heat would leave the fin if it were all at the base temperature. And this is just Newton's law of cooling, where H is the heat transfer convection coefficient, A sub F is the total surface area of the fin, and then theta B is just our base temperature minus T infinity. So while that equation it has some things that may seem a little bit foreign, it's all just comes down to Newton's law of cooling. So we're going to skip over, we won't deal much with irregular shaped fins, but we can skip down to another term which is similar to the fin efficiency. It's another way of measuring how good that fin is, and that is the fin effectiveness. So that is epsilon sub F, and that is defined as, again, that same QF. You would just take your fin, you would calculate QF based on something from that table. But now this definition is a little bit different. So this is the actual fin heat transfer rate. And then the denominator here is the heat transfer rate if there were no fin. So do you expect this number to be larger or smaller than 1? I'm hearing whispers of larger. Does anyone feel really like they really know what's going on here? So if I'm looking at some big sheet of metal, and I define sort of an area of this metal where I would put a fin. So that has limited surface area, right? So it's only going to convect a certain amount based on basically this fin's footprint. But if I add an actual fin on there, now I've drastically increased the surface area, which means I'm going to transfer a lot more heat now that I have the fin. So having the fin there means you get more heat transfer. If you don't have a fin there, it means you get less. So this is going to be a number greater than 1. And it's just a parameter that you can use to figure out and maybe to compare different designs, which one has the better effectiveness. So the efficiency is going to be a number between 0 and 1. The effectiveness will typically be a number greater than 1 because it's the ratio of how good the fin is relative to not having any fin at all. Any questions there? Q will vary with x, except where typically this QF is that refers to just the total amount of heat leaving the entire fin. So while the flux will vary with F and the heat going through the cross-section of the fin will vary, we typically don't care about that. We'll just talk about the total amount of heat leaving the entire fin, including the tip and all the sides going around. Any questions so far? So really fins, we have these nice convenient equations to help us analyze how would adding extra surface area onto our solid increase how much heat is being propagated. So you can define a fin resistance, and that takes on basically the same form. So the resistance is, for a single fin, is just 1 over H times A, but now because the whole thing isn't all at constant temperature, we have to factor in the fin efficiency. We won't use that thermal resistance for fins quite as much. Okay, so again, back to these solutions to the fin equation. When you have a fin and you can identify all these different parameters, then it's just a matter of plugging and chugging it into these equations. Those equations came from integrating that fin equation, and they just, in most cases, it's probably things you couldn't do off the top of your head. I know I couldn't, except maybe the infinite fin that ends up being just exponential dependence.
Just checking. So they integrated to get the temperature distribution, and then they also integrated again to get the time factor.
Yeah, well, they basically integrated all the flux down the whole thing to get the total heat transfer rate. Yeah. Okay, so if you're thinking about, like, if you want to design a system that is able to remove a lot of heat, you probably want more than a single fin. You're going to want to put a whole bunch of these things on there. So then we start talking about arrays of fins, and that just means you have many more fins that are all propagating heat, so you get a much better effectiveness. So when we do that, we end up with these other terms. So now we've drastically increased the surface area of our solid. So our total surface area is just the number of fins multiplied by each individual fin's total surface area plus the remaining area of the exposed base. So this A sub B is going to take into account this kind of area where there is no fin. There is still some heat transfer there, so we have to factor that into our total area. So to get the total heat rate is a matter of just summing up all the different places where heat is leaving our system. So here we have what's leaving from our fins. So this is QF total for all fins. So we have the total number of fins, the fin efficiency, the convective heat transfer coefficient, the total fin area for a single fin, and then our base temperature. And then this term is just the Q from all the base area that does not have a fin on it. Any questions here? So these are kind of plug and chug type problems. Yeah?
Does this kind of ignore the fact that if S was small enough, then that convection wouldn't work as well because it starts to actually heat up the air rather than the air being cooled?
Great. Yeah, that's a great question. This basically assumes you have a uniform heat transfer coefficient over your whole system. Where thinking ahead to convection, you're definitely going to be disrupting the airflow. That's an excellent point to make. So it's based on the assumption that your H is the same regardless of where you are on this system, and that may be a good approximation in some cases. In some cases, it may be something that kind of falls apart. So these are really, we're dealing with some extreme kind of simplifying assumptions here. Whereas if you actually became a design engineer of some sort, you'd probably get to the point where you're actually solving this kind of a system in 3 dimensions using some software. And that's where we're going on Wednesday. So those same kind of ideas that still apply. Now we can talk about an overall surface efficiency. So that overall surface efficiency is basically how much heat you actually transfer. So how much total heat you transfer divided by how much total heat you would transfer. So how much total heat transfer if the fins were all at the base temperature. So a perfectly efficient system by this definition would just mean all your fins and the whole thing remains at the base temperature. It conducts heat so well that everything is all at the base temperature, and then that heat, you still maintain a really large driving force for convective heat transfer over the entire surface area of your array. We also will get to effectiveness, which takes on the same kind of an idea. I thought that was coming up sooner. Okay. So when we're dealing with fins, this idea of a thermal circuit can also apply, where you're going to have some amount of heat transfer going through the fin, that Q sub F, and then some of the heat transfer going through the base. I'm not particularly concerned about this kind of stuff. You could also factor in this having a contact resistance. Maybe if these fins were not manufactured as one complete whole, but maybe you screwed them in somehow and you didn't have this perfect contact resistance, so you might pick up a thermal contact resistance going from the base to the fin, which would give you this extra resistance for the fin, while you just have this single resistance going through the base. Anyway, I'm not going to dwell on this because I don't find it to be that important. Oh, and that's the end. Okay. So I thought I had this in here. So let's also define the effectiveness of the array. So that's basically going to be how much heat transfer for the array divided by how much heat transfer if there were no fins. It's basically saying if I just left this surface alone without adding any extra surface area, how much better could I do if I installed a bunch of fins to increase the surface area and heat transfer. So that, again, is going to be a number that is greater than 1. Okay, so hopefully these definitions and that table will really help you on your homework problem number 1 for this week. So you're given an array of fins, and first I ask you to go through and figure out all these parameters for a single fin. So you need to solve for the temperature distribution, which should just be plug and chug from equations from that table. Then you would calculate the total amount of heat transfer from that fin. Then we look at analyzing the entire array. And really the important things to remember are, I find it helpful to remember these conceptual definitions of efficiency and effectiveness. So again, efficiency is how much heat you actually transfer versus how much you would transfer if the whole array were at the base temperature. And effectiveness is how much heat you actually transfer divided by how much heat you would transfer if there were no fins on the surface. All right, so that takes us to the end of chapter 3. You'll notice, if you're actually reading the book, you'll notice that there are sections that I'm skipping, and I've listed the sections that we're skipping on the syllabus. So if you're intellectually curious, go ahead and read those, but I promise I won't ask homework or exam questions on those topics. So now we're going to be transitioning into chapter 4. So in chapter 4, we're going to start dealing with two-dimensional conduction. So things get more complicated here. Okay, so chapter 4 is two-dimensional steady-state conduction. So in all these problems that we're solving, we've made assumptions, we've neglected heat transfer in 2 out of the 3 dimensions to reduce our problem down to a single dimension. That makes it much easier to do the integration and solve our problem. In this particular case, we're not going to be able to do that. We're going to encounter problems where heat transfer is very obviously happening in 2 directions, and we can no longer neglect thermal gradients in a certain direction. We have to account for them and solve for them. So these are going to be a little bit more rigorous. So 2 dimensions, imagine you have a solid where you get these isotherms. So the isotherms are here, these lines going down vertically for the most part. So we obviously have temperature changing in different directions. There's an obvious temperature gradient going in this direction, but there's also gradients going in the other direction. That means our flow of heat is also going to be two-dimensional. And when we apply Fourier's law, we need to account for the vector form of Fourier's law when we talk about how is heat flowing in these 2 different directions. So there are certainly various solution methods, and those of you who have taken partial differential equations have encountered these kind of problems. Because this is two-dimensional, we're still neglecting one of the 3 dimensions, but in Cartesian coordinates, if we have generation, we might be dealing with this particular form of the heat equation, where we've neglected changes with temperature in the z direction, and we're still talking about steady state, so we've neglected our accumulation term, but we still have to deal with those other 3 remaining terms of the heat equation. So there are various ways to solve this. So we could look at exact methods. So section 4.2 of your book will go through certain cases and how to solve these problems with exact analytical methods. You can also look at graphical methods, and then there's my personal favorite, which is going to be approximate or numerical methods. Again, today's society has advanced so much in computing. So if you remember when we derived the heat equation and we took our imaginary solid and broke it up into tiny little cubes, and we applied an energy balance to one of those cubes, and then eventually we shrunk that cube down to be purely differential. So it has no real dimensions. We took the limit as delta x, delta y, and delta z all go to 0. So that means our energy balance basically becomes these infinitesimally small little blocks. Well, if you have a fast enough computer, you can keep those blocks to be of a finite size, but really, really small. Then solving your system, you can actually use a computer to solve that energy balance for each individual little cube. And you can figure out, it's still an approximation, but you can figure out what the temperature of each individual little cube would be, and you can get these really detailed maps of how temperature varies through your solid. So to get closer and closer to the reality, you would just make your little cubes smaller and smaller, which means you're going to get more and more equations and more things to solve. But computing has advanced so much that computers are really powerful, and we can actually solve those kinds of problems now with just purely software. So when you're dealing with software and numerical methods, you don't have to whittle your problem down by making all these simplifying assumptions. You can just try to get it a reasonable size that you're not solving. Well, actually, you could actually solve millions of equations with millions of unknowns and get very, very near to a pure continuous system. So I want to emphasize those kind of methods, and that's going to be our focus on Wednesday. And I've talked about all these awesome computational tools, but we'll be using Excel. But really, it's the idea and the concept. And I want to show you how a tool as simple and ubiquitous as Excel can really tell you a lot about heat transfer through a solid and two-dimensional heat transfer even. Okay, so with exact solutions, when you have to actually solve, hopefully a lot of you have gotten familiar with solving PDEs. I have personally blacked all that out from my memory. So that was a joke, by the way. So you can really only solve these problems under a certain very distinct set of assumptions. So if we have a solid that varies in 2 dimensions, and again we're dealing with this term theta, which is just a reduced temperature. So it's basically just theta, I believe, in this system is just our temperature minus some reference temperature. So if we know that one side of our solid is at the highest temperature and all 3 other sides are at the lowest temperature, then we can solve that version of the heat equation analytically and get a solution that looks like this. Oh, I lied here. Theta is actually defined down here. So it's a reduced and normalized temperature distribution. So that's what our solution looks like. So our temperature distribution, represented by theta, is equal to an infinite series of these trigonometric functions. So if you want to go see the exact derivation, you can certainly go do that on pages 231 to 235. But if you know that your system fits this exact set of circumstances, well, good for you. You have this equation that tells you exactly how temperature varies at any point in your solid. So, and this is how our temperature profile would look. So you would see our highest temperature here, and then we're going to have these isotherms going out this way, and our temperature gradually decreases as we go out to each of the cooler sides. And then we're going to get these heat flow lines going in this direction. So our heat is generally going to propagate away from that side that has the highest temperature and toward the other boundaries that are cooler, just following Fourier's law. So that can be really complicated to solve. On the other end of the spectrum, there are these extremely simplistic methods that you can use to approximate the flow of heat or to maybe even solve for temperature. So these are called this conduction shape factor method. So the conduction shape factor method, again, you can only really use this in certain scenarios, but it's when you have 2 or 3 dimensional heat transfer and you have one solid that you're assuming to be isothermal embedded in another solid. Often it's going to be semi-infinite and it's radiating heat. I mean, it's conducting heat out to the surfaces of that solid. So let me just help you get a flavor of this. So this is one where you have a cylinder that's buried in a big square. So this is obviously a two-dimensional heat transfer problem if the temperature here is higher. So if this is hot, you're going to have heat going out this way. You're going to have heat going out this way. You lose the symmetry here because you've got these corners to deal with. So this is obviously a two-dimensional heat transfer problem. So what this shape factor term allows us to do is if we make the approximation that this T1, or the surface temperature of this embedded solid, is all the same, and that T2, the surface temperatures of the other material that's embedded in are all the same, you can write heat transfer in this form. Again, this is an extreme approximation. This is basically saying that the flow of heat from shape 1 to shape 2, all the way to the surfaces of shape 2, can be written in this form. So it's S, where S is called the shape factor, times K, where K is the thermal conductivity of shape 2, multiplied by this temperature driving force. So all this is somebody has gone through and has solved the much more rigorous form of this problem, either analytically or numerically or experimentally, and then they give you these correlations to say, okay, if you want to know something really simplistic, like just the total amount of heat transfer from shape 1 to shape 2, this is it. So you're still probably wondering what on earth is a shape factor. So this is something you would go look up from a table given your particular system. I'm going to skip this in the interest of time because I want to get to, I don't love this shape factor method. It doesn't give you a ton of really good information. It's really overly simplistic. But you can go look up, I'm going to skip this problem. So here's a shape factor example. So I hope to teach this a little bit better by example. So if we have an electrical heater that is cylindrical in shape embedded into the ground, and we want to know either how much heat is leaving our heater and making it to the surface, or we're given how much heat is going into our heater and we want to solve for the temperature of this heater, well then we could go look up a shape factor for this particular system. So if it's a problem where you're given these certain assumptions, that we can assume that this surface is all isothermal, and then the ground surface is also isothermal. So our T1 is the cylinder itself, and then our T2 is going to be the surface of the ground. We would go look this up in a table that looks like this. So this is table 4.1 in your book. I'm just showing you a few of these. But of those 4, which of those looks like the system from our example problem? Yeah, case 3. So then all you do is you find the different dimensions. You look up your shape factor, which in this case would be 2 pi times the length of the cylinder divided by the natural log of 4L divided by D, where D is the diameter of the cylinder. So that gets us the shape factor, which is just our S. Then we can take that and just plug it into this equation. That particular problem is asking us for, if you read it all the way through, it says, estimate the temperature reached by the heater when dissipating 50 watts with the surface of the block at a temperature of 25 degrees C. So our equation was Q equals SK times T1 minus T2. So by using this shape factor method, we can just go look up what our S is, do some plugging and chugging to get it in that form. We know the thermal conductivity of our system. So that's known. That's known. Our ground temperature is 25 degrees C, so that's known. And then our unknown is T1. And our known is just Q. Q is given to us here. So basically you just take this equation and apply it. I don't love this method. You have a couple of homework problems just to help you get used to it, but the simplifying assumptions here are so extreme that I don't find that you get a ton of value out of solving something like this. You'd get a sort of a first order approximation as to what temperatures you'd expect. Okay, we're going to skip that one too, because there's another form for when you have a solid that is at uniform temperature and it's totally embedded in some other material. That other material is now all uniform temperature. You can take a very similar approach and use this dimensionless conduction heat rate, that Q underscore SS, and do the same kind of thing. So this is basically the same kind of an idea, and there's another table where you can look it up, look up what your QSS is, which is this dimensionless heat conduction rate. So again, this is basically the same kind of a thing. It just takes on a little bit different functional form. So these make for really overly simplistic problems, and whenever the problem is really simplistic, it means the information you get by solving that problem is going to be a rough approximation of the reality. So another area, so on one extreme we have trying to solve the two-dimensional form of the heat equation analytically, and that's very restrictive. Only under certain limiting assumptions can you actually get a true analytical solution, and it gets very complicated even then. Then on the other extreme, you have this shape factor or dimensionless conduction heat rate. So somewhere in the middle lies this finite difference method, or using a numerical method to solve these kind of problems. And this comes down to the same skill I've been trying to get you guys doing, is just defining a system and putting an energy balance to that system. So in this method, this is very similar to how we derive the heat equation. The only difference is that instead of shrinking down our volume down to be infinitesimally small, we just shrink it down to be small but still finite. Then we apply our energy balance to each little cube or each little shape. That gives us several equations, maybe even hundreds or thousands of equations that all represent an energy balance, but then we can solve all of those equations simultaneously to get something like their temperature. So this is what we're going to go into on Wednesday, but basically same kind of an idea. You just define a control volume, you put on your energy accountant hat, and you start figuring out how is energy getting in and out of each one of those little blocks. And if you get good at this and you have a really good systematic way of thinking, this can be an extremely powerful tool that can really approach the real solution as long as you make your control volume small enough and have a fast enough computer and efficient enough coding skills to solve it. So what comes next in these slides are doing this method in Microsoft Excel. Excel is limited. It can only handle about 100 equations and 100 unknowns, so that's what we're going to do. So watch the 2 lecture videos. So Wednesday we're going to flip the classroom, which means I expect you to have watched the lecture videos before you come, because I'm going to dedicate Wednesday to helping you solve your homework problem, it's problem number 5 of homework 3. So watch the lecture videos. They're actually listed in the homework. I also posted them on Canvas. So go watch those. It'll walk you through how to do this method and how to apply a numerical method to solving the heat equation. Thank you.